Good morning. Are there questions on material or homework, previous homeworks?
Only big question I got, when's the final? Is it Saturday morning?
Yes, I will send an announcement. Yeah, it's scheduled. It's Saturday morning. The official time is 7:30 to 9:30, and I'm thinking about posting it a little earlier and giving you a little more time. But given that the next final is, I think, 9:45, I don't really want to intrude into the next final. But given that you need to download it and upload it, etc., I'll probably start maybe 7:15. I'll be posted, so you have time to download it, and I guess 9:45 probably will be the actual deadline. But I will send an announcement with all the details. The modalities will be the same as for the midterms.
Thank you.
Okay. So there is a question whether you only have 2 hours to complete and upload. Well, I'm a little ambivalent about that. I'll be happy to give you much more time than that. The problem is any student who has a midterm, as a final at 9:45 will not be able to avail himself or herself of that extra time, and that's a little bit of a problem. I guess I could ask the class if anybody has a final at 9:45, but even if just one of you has it, then that's an issue, right? I can certainly do that. Let me make a note. Okay. I'm afraid that given that the class is so large, there will be someone who has a final then. So we'll see. I'm actually sizing the final according to the fact that you do have 2 hours, which, by the way, would be the normal time if we didn't have the pandemic running around the country. So 2 hours is normal. And I'm not asking anybody to typeset, although that's wonderful. I guess I could give some extra time to anybody who wants to typeset the homework, just because that makes it easier to read. But that's about it. We'll see. We can discuss this maybe when, maybe through announcements, etc., because the class is much larger than the current number of participants. So no, so there's a question. No, the final is on everything. It's not just on the new material. The final is on regular, context-free, and Turing languages. All right, so you're welcome to ask questions. Again, I always ask if you can speak up instead of type. That's easier because from this distance, I can barely see the chat. Not just because I'm old, but because I have a laptop and the font is quite small. Okay, so today, Wednesday and Friday, pretty much it will be just training for the final, meaning we're going to just go over exercises. I hope that I will get requests from the audience about exercises. Of course, feel free to ask about any previous homework exercise, what is the best answer, what is an alternative answer, and so on. I have my own big set of notes for exercises, and I can go over those. If you have any problem from the book or somewhere else that you want to go over it, hopefully I'll be able to do it, and we'll do it together. But what I want to focus really will be what is a really good answer, not just a barely passable answer. As I said, some of you are really losing few points here and there on things that you really could do better, and the final is a large portion of your grade, and also being the last and perhaps more representative type of assignment that you are doing. If you're doing really well in the final, I can't believe that you actually learn most of the material. And so that might raise your grade really quite a bit. So this week, all we're doing is, just like if we are going in a competition, in a sports competition on Saturday, we are just training, okay? And even if you're doing well in the class, I strongly suggest you attend this week, because doing well and doing really well and doing really, really, really well is not the same, okay? All right, so all I have to do today of new material, which is not really new, is just this little last portion here, which I already have done actually in class, right? So I guess this summarizes the entire content of the course. All right, so we have, this is the class hierarchy. Right, so we have regular languages, we have deterministic context-free, then we have context-free languages, then we have context-sensitive languages, then we have TDL, Turing decidable languages, then we have TAL, and of course, not even TAL, okay? So this is the classic hierarchy you will see in any course on undergraduate formal languages. Now in this class, we actually saw a few additional like classes. We actually saw a class which is smaller strictly than the regular languages, because there was this bonus question about decision diagram, MDD, BD, etc., right? Those are languages that contain strings that are all the same finite length. A little more general than that, but still less than regular, are just the finite languages, right? So any language that is finite is, of course, regular, but is a special case of regular. So, question for the class. Can anybody give me a characterization? What is special about finite languages as opposed to regular, normal, regular languages? What is special about, for example, their the final automaton, let's say the DFA, that assets a finite language. How does it differ from the generic? What is the restriction it must have?
Will never be any looping.
Except on the trap state. Very good, right? Okay. Let's see. So this is a trivial new one, right? Finite. Well, not new one, but it's one that is not often explicitly discussed. But we did it because all MDDs are set exactly, or can use to describe exactly a particular set of finite languages, the one where all the strings have the same length. Then we saw another class which is normally not seen, right, in this course. Again, optional. And those were the Patronate languages. Well, let's put them away, PNL, right? And we saw that Patronate languages include all regular, and they have a common intersection with context-free, but there are some context-free which are not PNL, there are some PNL which are not context-free. And they are kind of interesting. I certainly like them. I work a lot on them. Okay. Then the only other thing is the question there is deterministic context-sensitive languages, which are those that are accepted by linear bounded automata, right? Linear, not deterministic linear bounded automata can accept any, well, the class accept this context-sensitive language. They're exactly the same thing, the same class of languages. Now, if you restrict the linear bounded automata to be deterministic, it is not known whether the deterministic CSL, which is the class accepted by deterministic linear bounded automata, is the same class as CSL, or if it is a smaller class, right? It will contain all the context-free, but it's unclear whether this is a strict inclusion or not. And then, as an exercise, I'm not going to do it now, but in your spare time, you should be able to name a language in each of these sets. Right? So you should be able to name a language that is here, but not there, 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 and so on. Right? So you should be able to name at least one language in each of those classes. Okay? We certainly have seen plenty of those. All right, so any question on this? And by the way, for Patronate, there are really many classes of Patronate languages because it depends whether you're doing a set on a trap state, a set when you pass through or generate a string when you pass through a particular marking in the final, and then whether you allow epsilon or you're allowed to transition to the same label, etc. Right? But again, these are, you want to do work on Patronates, come see me after the end of the class, well, of the course. Okay, plenty of interesting stuff to be done on Patronate. So, but are there any questions on this class hierarchy? That's a big takeaway from this course, is really to understand the power of various models of computation in terms of the languages they can talk about. Okay, I hope that means that this is now cemented in your brain for the rest of your career. It's fairly important. So now we can start with the, I guess, the fall training, not spring training. All right. So unless there is any questions on homework 13, and by the way, homework 13 is due Friday morning before class. because I will go over the answer in class. Okay. Actually, let me send a reminder. Okay. All right, so if there are no questions on homework 13, I would like to start doing random exercises. And please, if you have any question about a good way to answer one of the homework questions, or if you have any questions about any exercise that you have encountered in this course, within the class or outside, please ask.
Can you go over a good answer for a reduction problem? It doesn't even matter what it is, just can you give an example of what a good answer for reduction would be?
Yep. Well, let's look at my infinite set of nodes. Let's see. Okay, that's a good one. All right, so the exercise is use reduction to prove that L equal rho of M rho of W, M does not return to its initial state when running on input W. Okay? And this question is undecidable. Okay? So again, always in your life, including for the final, really understand the question, because if you don't understand the question, you will answer the wrong question. So we're talking about the language that is the encoding of a machine and the encoding of a string. And we should say, we should accept, which means hold, because we're talking about acceptability, right? So undecidable means it's not acceptable, right? So the idea is we should, is decidable, is acceptable, but not decidable. Okay. So we need to show that we can accept this language, but we need to show that we cannot decide this language, right? And the language is what? Is if the string in input is the encoding of a machine M and the encoding of a string W, we should say yes or no, depending whether when M runs on input W, it passes through the initial state again. Of course, initially it is an initial state, but the question is, will it enter the initial state again? Okay, so first of all, if I want to accept this language, what do? I just simulate mu on omega, so on W. If M enters W, so if M enters the initial state again running on W, then I say yes, I hold, right? But of course, if M keeps running, for example, if M doesn't hold, I just can follow M computation, but I cannot ever say, no, it doesn't. Well, if that's all I do, right, if I just simulate M on W, I will not say no, right? So in other words, a machine that accepts this language is easy. It's pretty much is just the UTM, and then I just monitor whether the UTM modeling M says M just entered the initial state as its initial state as. But now I need to show that it is not decidable, meaning I cannot build a Turing machine that will say yes or no for the strings in input. Okay. Okay, so use reduction, right? So I'm gonna say if I could decide L, and I could decide K1 rho of M, rho of W, M holds on W. In other words, that's the halting problem, right? We know that the halting problem is not decidable. So I'm going to show now that if I can decide this, I can decide that. Okay, so again, when I need to do a reduction argument, the first thing to do is to pick a good language, in this case, the halting problem, and reduce it. Right? If I want to show that something is not decidable, reduce it to reduce it to this problem. The problem that I need to prove is not decidable. That's the first thing. You choose the bad language, and you will not be able to do much, right? Well, not a bad language. You choose the language that doesn't work for the proof. Then I need to give you the reduction. In other words, I need to show you that given an instance, so given an instance of K1, of this, well, of the problem K1, right? So I have an input for K1. We now modify it so that I modify it into an instance of L so that so let's call the instance X for K1. We modify into an instance Y of L so that the answer Y is in L can be used to answer whether X is in K1. Okay? So that's the idea of reduction. So now, what does it mean? You give me an instance of X, X of K1, which means you give me an M and you give me a W. Okay? And I would like to know, to decide, does M hold on W? Well, so M is going to be some Q sigma delta S, right? Set of states, input alphabet, the delta that describes the behavior of M, and the initial state, right? And then, of course, the question is, from S with blank, W blank, does M enter the halting state? Okay, so that's the question I want to answer. So what do I do? I build a Turing machine M prime that behaves like M, except I need to make two changes. I want to build M prime so that M prime enters its initial state again if and only if this machine holds. So here's what I can do. I can say M prime is equal to let's add at least S prime, maybe more, but we need to add a new state S prime, sigma, delta prime. We start in S prime. And then what does N prime do? From S prime, like this, in one step, M prime goes to so I added this S prime so that the initial state of M prime is not S anymore, is this S prime. And the only reason to do that is that, well, one reason to do that is that S is not the initial state anymore. It's just a normal state. S prime is the initial state. And then I want to know, does M holds, which means does it enter the holding state? So what I need to do now is, of course, to do this, I need to adjust the delta, right? That's why I have delta prime here, not delta, because this is an additional step. But then the other thing is, if from some P A, the machine M goes to H whatever, then the machine M prime does not hold, but it enters state S prime. Then I say from P A, M prime enters S prime. And I think that's what I need to do, right? Because I want to answer the question, does M hold on W? And I modify my machine so that it starts in some new state S prime, and when M would enter the holding state, M prime instead enter its initial state. And then M prime behaves exactly the same as M otherwise. So it just simulates M. Right? So now, what can I do? If I give M prime W, well, rho of M prime, rho of M prime, rho of W, to this machine that supposedly can decide this language, L, then I will get a yes or no if and only if M holds on W. So now I can use this machine that decides L to decide K prime. But we know that K prime is not decidable, so the machine that decides L does not exist. Okay, so that's a very clean, typical example of how to do the reduction, right? So you need to have the right idea. The right idea is this, essentially entering the initial state becomes the same as the original machine entering the halting state. But to make this clean, correct formal is that I don't want to use the initial state of M as the initial state of M prime, so I add this S prime. Okay? And then this works. So the first thing, the key thing is to have the right idea. Once I have the right idea, which implies I know which language I'm reducing to L, in this case, K1, then it's just a matter of writing it nicely, okay? And again, this is somewhat written nicely. Again, I'm doing it on the board. If I were writing it in English, in LaTeX, it would be probably hardly half a page. Now, let me tell you one thing which would be almost correct, but you would lose several points, and that is to say, I take M, and I just change this part. So if M would go and hold, I make it go instead to its own initial state, S. And then I could still use this, the same idea, and say, well, you give me M and rho of M, rho of W in input, and well, it's really an M prime because I modified it, right? And then if this M prime would hold, would enter then its own initial state, it means that the original M would hold because of this. What is wrong with that argument? It's almost right, but there is one little error. What is wrong with that? In other words, why do I need to add S prime and not just change in M the transitions to H into transition to its own S initial state? What's wrong with that?
Is it because you're not actually halting at that point? And you risk running through it again?
No. So what happens? I'm changing. So if M would hold, I change that it instead goes to its own state S, initial state S, right? Supposedly, I can decide whether a machine M, enter its own initial state S, but I know I cannot decide whether M also holds, right? Enters H. So what's wrong with just changing transition to H into transition to the initial state? There is one little detail that breaks your transformation doesn't. It's not true anymore that something is here if and only if something is in K1.
It doesn't fully prove the contradiction, and therefore
Why? What's the thing I missed in my trick? It's the same idea, right? But it's not implemented correctly. Why do I need to introduce this new state S prime? Well, it's possible that M, when it runs on W, it enters its own state S during the computation, right? But the question I want to answer here is not, does M enter S, is does M enter H, does M hold, right? So if I now change transitions to H into transition to S, I'm confusing because now when M enter S, it could be because it would have entered H and I not changed the transition, but it might be just because normally in its computation, S is normal state, right? So M would enter S. So I need to distinguish the cases where in the normal computation, M enters again its own initial state, which in K1, it's not a problem at all. It doesn't mean anything. From the case where M enters the initial state because it would have entered H instead, right? But I cannot distinguish those two unless I introduce a new state S prime. Okay? So again, this is having the right idea, but missing an important detail, right? So the important detail is I want to be sure that my new machine M prime enters its own initial state, S prime, if and only if the other machine M would have entered H. Not if it would have entered its own initial state, which is perfectly fine for a machine to do. Okay, is that clear? It's a subtle detail, but it's what makes the transformation work, or yeah, almost work, which means almost means no, right? Okay, other questions? Please keep them coming. I hope we can do this the whole week.
Can you go over just a somewhat harder problem for unrestricted grammars? Or is that not going to be?
Well, I was actually just looking at I don't know if it's hard actually, but let's look at an unrestricted grammar to generate a particular language. So an unrestricted grammar for the language WW. W is in 0, 1 star. In other words, it's not the palindromes WWR over 0, 1, which is context free, is the language where I have W and then W again. So I'm repeating a particular string, which we know is not context free because even using determinism, the second W is presented in the wrong order for a stack. Okay, all right. So let's see, I have an answer here. I need to see how it works. I did this a long time ago. Okay, so I'm using S, A, B, C, X. Let's see why we need all those. Oh, looks like there is an error here, so I'll have to fix it. Okay, the alphabet, of course, is 0, 1. The starting symbol is S, and the productions are P. So let's see if we can do this. So productions are, let's see, S goes to XC. X goes to 0, XA, or 1, XB, or epsilon. A0 goes to 0A, A1 goes to 1A, B0 goes to 0B, B1 goes to 1B, and then AC goes to 0C, B0 goes to 0B, no, I had that already. BC goes to 1C, and then C goes to epsilon. So I did this a long time ago, so let's see if I can remember how it works, hopefully. I think this is the idea, right? So you start from S, and you get, the only thing you can do, right, from S is XC. And then X generates a very famous language we have seen. What is the language that it generates? Well, if you think of A as 0 and B as 1, what language is that? It's just it's just the palindromes, right? If you think of this as 0 and this as 1, right? Because it's just 0, 0, 1, 1, always in the middle, and then eventually it goes away. So there actually is the even length palindromes. So from here, in other words, for example, I can do 0xac, and then again I can do 0, 1xbac. And again, think of the b as 1 and the a as 0. Then okay. Then the S can go away. 0, 1, BA, C. And then how does this work? I need to get rid of the B. Well, again, in general, here we'll have some string of 0, 1s, and here I will have the string of 0, 1s reverse, because these are the palindrome, where instead of 1 I have a B, and instead of 0 I have an A. And then I need to get rid of the B and A. How do I do that? The only way to get rid of B and A's is to make them go to the C. And look, here I can move A's and B's. So this all this says is just that I can move the A's and the B's to the right over 0 and 1s. I cannot move them over each other, because otherwise I would break the patterns that I want to generate, right? So here, what I can do, so B, right now I cannot do anything, but AC can become 0C. So I get 0, 1, B, 0C. Then what can I do? I mean, at any point I can, of course, do C goes to epsilon, but as soon as I do C goes to epsilon, and if I still have some B's and A's, that's it. I will not generate any string in the language because I will get stuck with some variables, A or B, right? So the only thing I can do is 0B, B0 becomes 0B. So I have 0, 1. Sorry. Right. 0, B, C. then BC can become 1C. 0, 1, 0, 1, C. And then C can go to epsilon. And I get my 0, 1, 0, 1, which is the W, W. Okay, so the idea, again, for this kind of problems, you need to have the right idea, right? So the right idea here is I generate essentially WW reverse, except the first W is a string of 0 and 1s, as it should be. The second W reverse is a string of A's and B instead of 0 and 1s. But that's not a problem. I could just have A goes to 0 and B goes to 1. But I don't want to do that because I need to reverse the WR, right? So in other words, informally, I'm generating W reverse C. And then, again, this is where I'm mapping 0 to A's and 1 to B's. And then I need to, from these, I need to get the W, right? And so the idea there is I move the A's and B's from the left to the right. So essentially I'm reverting the W, R into W. And to do that, I just had put my C at the end. And so they only change, they move and they become the 0 and the 1s as they get to the C. And so here the trick is the A's and the B's can move over 0 and 1s, but they cannot move over other B's and A's. Because if they could, I would mess up the pattern. So here, I can essentially change them in this order from the right to the left, and they become left to right, right to left. Is that clear how it works? So that's a typical example of the power of an unrestricted grammar that essentially let me move things. Don't be afraid of using additional variables like A and B in this case. I cannot move just digits, right? If I only had the digits at the point of 0 and 1s, it would be too late, right? But this way, I can distinguish essentially with the A's and B is the second half. So the key idea is use context-free ideas here to generate almost what you want, except you need to revert it. Okay. And as always, it's easy to see that you generate all the strings in the language. You also need to convince yourself that you don't generate strings that are not in the language, of course, right? Otherwise, I could just generate the regular language 0, 1 star, and all the strings in the language are there, but also all the strings not in the language are there, right? So you need to be sure that you don't generate strings outside the language. Okay, that was unrestricted grammar. Think about question, and please think about question for the next 2 classes as well, okay? All right, while we wait, let's do a simple one. The file is on everything, even on simple things, right? So regular grammar. This is as easy an exercise as you can hope to see. Okay? So the rules of production, I put R because rules are often called as well for production, right? Are just these 3 productions. And the question is just, give me the regular expression for this, for the language generated by this regular grammar. I'm going to wait for the answer from you, right? So I start from S. I can only apply this one. And then I can only apply this one. Well, actually, I could apply S goes to epsilon, of course, right? And then I keep going, and eventually the only way to stop having variables will be if I do S goes to epsilon.
AB star.
AB star. Well, with a parenthesis in the right place, right? This AB star, not this AB star. Right? Yes. So in English, the language that contains 0, 1, or more repetition of the string AB in order. Okay. But don't sneeze at this. By now, since we're looking at these very complex questions, these are the easy questions, and you have 2 hours. You should spend 5 minutes on the easy questions, and then spend an hour on the harder questions, right? And maybe have some time to spare. Okay. If you have questions, please ask. Okay, this was from apparently homework 6. Let's go over it again. So and define an MPDA for L equal A to the 2n, B to the n. So when I read your homework, you often use the word string, which is not wrong, but you should use run. When I say something like, is this language of strings containing a run of A followed by a run of B? So a run means a substring inside, a contiguous substring, right? Where the run of A is twice as long as the run of B, okay? So just to be clear, the strings in this language have length that is a multiple of 3. So epsilon, AAB, A4, B2, A20, B10. Okay, all right. So let's draw the MPDA for this. So the idea is, again, when I draw an MPDA for something like this, I draw it, and maybe I fix it a little bit if I make any, not as a mistake, but I need to take care of some special cases, right? Sometimes I don't make any mistake right away, but who knows, right? So here, one way of thinking about it is I need to count the number of A's by pushing them in on the stack, right? And so I can just say, if I have an A, push A. Then when I see a B, I can stop, but it's actually lazier, easier to just say, I have an epsilon transition to go to this state, where now I need to pop the B's, right? So pop the A's corresponding to a B. So if I see a B, what do I need to do? I want to pop an A, right? So if I see a B, I should have an A on the top of the stack. But I should have really 2 A's, one after the other. So how do I do that? Well, I should have really write pop A here. That's not right. Or pop A. But I go here, and then I go here, and I say what? On epsilon, pop an A. Meaning, if I see a B, I should be able to pop A and then pop A again. And that's the way to pop 2 A's, right? and then I see another, I should be able to do a third. How do I go to a final state? Z is the bottom of the stack, right? If you want to be extra precise, you write the definition of MPDA where the stack alphabet is what? Just A and Z, and then you pop the Z, right? The Z is the initial one. Okay, so this works better than if I said, so this is non-deterministic, right? Because, well, why? Because as I'm pushing A's, I'm just deciding epsilon just means don't touch the stack, right? Just leave the stack the way it is. I go here. And maybe there are still some A's. So if now I see an A there, what happens? Well, I die, which is fine. Okay. You might want to be extra zealous and say, well, no, I want to move out of A only if I see a B, right? Which would make sense if you want to be deterministic. The problem with that is that then you go there on a B, you really should go probably here on a B, right? But then and you pop an A, and then you pop the other A, and then you keep doing this. But then the problem you need to be careful is what? What is the problem? So, okay, if I, instead of this transition, I had this transition, B, pop, A. What is the problem? That's almost right, but it's wrong again. Almost means not, right? So it's very little wrong, but it is wrong. What's wrong with that answer? It's a small error, but it's an error nonetheless. Okay, so I don't have this, I have B pop A there.
It doesn't consider the case where n is 0.
Right, it doesn't accept epsilon, right? It does not. This one, epsilon, epsilon, it lets me go to the final state right away. And then that's fine, because if the input string is not epsilon, the string is not accepted because on that clone, because the definition of an MPDA is that the string is accepted if it is completely consumed and I am in state final, in a final state, right? So this one sets the right language except for the epsilon, right? So it's a small error, but it is a little error, okay? And in a sense, it's an understandable error because it's an error, we like to think deterministically as much as possible as human beings. So certainly the idea here is I switch from pushing A's to popping A's when I see the B, right? So that's right thinking, but I need to fix this. So one way to fix it would be, I guess, to go from here to here on an epsilon, pop Z, but then you really have added more complexity than this, right? This is perfectly good. MPDAs, non-determinism is really useful. Sometimes it makes it more understandable, actually. Okay.
Is there a way to deterministically pop two A's for every B you see?
Deterministic pop, you mean, is there a deterministic MPDA for this?
Yeah, or more specifically for like if we're looking at the right side of this part where every time we see a B we pop an A and then we see an epsilon we pop an A. What would be the way to do that deterministically?
Well, no, okay, so but this is the deterministic, this part, even if I have an epsilon, right? Go back and look at the definition of deterministic pushdown automaton. And a deterministic pushdown automaton is one where you don't have two outgoing edges from a state labeled with I need to have A input and X on the stack, right? Then if you have 2, then you have non-determinism. And if you have something, you cannot have epsilon, right? So if you have an A pop X, you cannot have an epsilon transition. But you can have an epsilon transition if that's the only thing you have, right? So otherwise, you couldn't be able to count 2, right? So this is perfectly fine in a deterministic Push-down automaton. This one is not, right? Because here, if I am here and I have an A in input, I can either do A push A or this epsilon transition. So that's the only non-determinism in the black, not the red. Right? In the black version, this is a non-deterministic behavior. Now I hope, so that answers your question, right? So this is perfectly fine. This is determinism still. Determinism, think about it, means I can only do one thing in a state on a particular input, right? And here, when I'm in this state, for any input, the only thing I can do is ignore the input and do the epsilon. So that's determinism. So that's fine. I must have A. If I don't have A, it means the string is on the language, which is fine. Now, the related question is this acceptable deterministically? And I'm pretty sure it is, because think about it. One way I like to think about, right, is I could just write a program that just uses the stack and it's a deterministic program, right? It's a C program. And essentially, you just match these, right? So now the question here is, how do I deal with the epsilon problem, right? So this part, it's good to set everything except for the epsilon, right? So these are sets A to the n, B to the n, where n is a positive integer. So if I wanted to, right, so for example, this is deterministic as well, right? Because this says, it's true you have an epsilon transition and a B transition. However, I can do this only if I have A on top of the stack, and I can do this only if I have Z on top of the stack. So that's perfectly fine. Let's see. If I make this final, that's not quite right, because
Couldn't you just add
then I
a
set
before
AA, for example, right? I set a string just of A's. Sorry, someone will give me a suggestion?
Couldn't you add a state before the start state that accepts and then move into that state when you see an A?
Probably. I think that's what I need to do. I think that's what I need to do is this. I think this will make it deterministic, right? Because, so these are sets epsilon, that's good. And then the only thing I can do from here is, if I see a B, I die, I don't want to do that. But if I see an A, I push it. And then from then on, I don't need to worry about a set in epsilon. So that's the right answer, very good. And again, be careful, my initial suggestion was, the lazy one is, let's see if this works by making this final, but it doesn't. It doesn't, because then you would have set a star plus this, and I don't want to do that, right? But that's good. That should fix it. So, in other words, this is a deterministic language. It's pretty obvious, right? It's as you parse, you know exactly what you need to do. When you see the B, you need to start matching. So it's just writing with a deterministic push-down automaton. Very good. Wow, sorry, it's 9:55. I guess we're having too much fun doing exercises. Okay, well, we were 15 minutes above the limit. I'm sorry about that. Please come with questions for next class. We're having fun, I guess. Have a good day.